Assalamu alaikum dear students, welcome back to my channel. In today's lecture we are going to apply the alternating series test that we have proved in our last video to investigate the behavior of different alternating series that we have been given here. Okay, but before that I would like you to subscribe my channel if you haven't yet and hit the bell icon as well so that you don't miss any update in the future. Thank you so much. Alright dear students, let's start with our first example. So here we have an alternating series and it has a special name. It is sometimes known as the alternating harmonic series. Okay, so we are going to investigate its behavior. If you can recall the two conditions of the alternating series, the first condition was that the size of the terms of the series should be decreasing as we move on in the series. So first of all, we are going to check whether it will happen with this series or not. Okay, if I ask you to consider any two consecutive terms of this series, what will be it like? Okay, it will be like if I take 1 over n to be a term of this series, the very next term will be 1 over n plus 1 if we ignore the sign, of course. As you can see from here, the numerator in both of these fractions is same, but the denominator is changing. Okay, the denominator over here in this fraction is larger as compared to this one. So what will be the size of these two fractions? If you compare the size of these two fractions, you can easily conclude that the one with the denominator larger in size will be less than the one with denominator with size less than that one. Okay, so we can easily say that 1 over n will be less than 1 over n plus 1. So what does it tells us? It tells us that every succeeding term in this series will be smaller in size as compared to its preceding term. Okay, and what does that mean? It simply means that the size of the terms of series is decreasing as we move on in this series. Okay, so our first condition is satisfied. C1 is now satisfied. First condition is now satisfied. And now we would like to see whether the second condition of alternating series test holds as well or not. Okay, what was the second condition, by the way? It was to see whether the limiting value of the terms of the series is 0 or it is some other thing. Okay, so let's investigate this. The general term here in this series is 1 over n. And I'm going to look at its limiting behavior. Okay, so let's take the limiting behavior, consider the limiting behavior of this term as n approaches infinity. It means we are actually taking limit n approaches infinity of 1 over n. And from your basic calculus course, you easily can find the answer to this question, which is in this case 0. Okay, so C2, the condition 2 of alternating series tests, is also satisfied. Okay, as both conditions of the alternating series test are satisfied by this series, so finally we can conclude that the given series, I'm talking about this one, is actually convergent. Okay students, now here we have another example of an alternating series. Let's see how it will behave, whether it will converge or diverge. So if you look at the general term of the series, it is, if I write it as an, the general term here is n square over n cube plus 1. Now there are two methods that can be used to check whether the size of the terms is decreasing for this series or not. One is to just simply look at this expression, okay, and the other is to construct a corresponding function and then investigating the behavior of that function, and then from there concluding that this series is actually as we want. Okay, the size of the terms is decreasing. Okay, so let's see. If you look at this expression, this fraction n square over n cube plus 1, we are all aware of the fact that squares are always less than cubes. Okay, And even in this case, it's not just the cube, it's n cube plus 1. So it is even bigger than n square. And it's over common knowledge that if you have numerator which is smaller than the denominator, in that case it will always be less than 1. Okay, the answer to this fraction will always be less than 1. Okay, and as much as you increase the value of n cube, this size will keep decreasing. Okay, so from this fact, from this argument, we can conclude that the size of the terms of this series is actually decreasing as per our requirement. The other way to check this is to construct a corresponding function. That corresponding function in this case will be x square over x cube plus 1. X square over x cube plus 1. Okay, we just need to check the behavior of this function, whether it will decrease or it will increase. Okay, to check this we will apply our techniques from calculus. Okay, and then as I have done this in my rough work, I have concluded, and you can conclude as well. I'm inviting you to do this by yourself. Okay, you will see that this function is actually decreasing in this interval, third root of 2 to infinity. It's decreasing in this interval. Okay, and this shows us that the size of the terms of this series is actually decreasing. Okay, now as far as, because it starts from 1 point something, so we are sure that from 2 to onward the size of the terms is decreasing. But what about between the term 1 and term 2, first term and second term? So you can simply evaluate it for term 1 and term 2, and from there you will see that a1, the first term, is greater than a2. But since we are unable to do this for every single term of this series because it contains infinitely many terms, so we avoid this and then simply perform this calculation. We simply adopt this strategy to check whether the size of terms is decreasing or not. All right, so one thing that we have concluded so far about this series is that the terms are decreasing in size. So our first condition of alternating series test is now satisfied. C1, the condition number 1, is now satisfied. Now there is only one thing left for us. We need to check whether the limiting value of the terms of this series is approaching 0 or not. Okay, so let's investigate this. Taking limit of the general term as n approaches infinity, n square over n cube plus 1, this is our general term, and if you take this term, you can easily see that its limiting value as n approaches infinity will be 0. Why? Because as the number in the denominator will increase significantly, the answer will become closer and closer and closer to this 0. Okay, or you can apply your simple limit finding techniques. Okay, for example, you can write this like, I would like you to divide the numerator as well as the denominator by n cube. Okay, so let's see how will it work. Limit n approaches infinity, so dividing numerator by n cube as well as denominator by n cube, we will have this expression, and then simply cancelling the terms, we will have limit n approaches infinity 1 over n over 1 plus 1 over n cube. So if you simply put the n as infinity, what will you have? You will have numerator as 0 and denominator as 1, which will give you 0. So it's up to you whether you can compute from here or you want to perform these steps. That is totally up to you. That is up to your understanding. Okay, so condition 2 is also satisfied by this series. I can write it from here simply that C2 is also satisfied. So both the condition of the alternating series test have been satisfied by this series. From there, finally we can conclude that this series is convergent. Alright, dear students, so we have another series right before us. So let's see how will it behave. First of all, I need to check whether the size of the terms is decreasing or not as usual. So I would like to do this using the technique of comparing the two consecutive terms. And what I am going to do, I will take the quotient of any two consecutive terms of the series and I will check whether its answer will be greater than 1 or less than 1. If the answer is less than 1, then it simply shows that the size of the terms is decreasing as per our requirement. But if the quotient is giving us the value which is greater than 1, in that case it simply means that the size is actually not decreasing, and from there we will announce our verdict that this series is divergent. So let's see how will it behave. I'm going to compare the two consecutive terms, and those two consecutive terms in my view will be ak plus 1 and ak. Okay, so what is the k plus 1th term of this series, excluding the sign of course? It will be k plus 4 over k plus 1 into k plus 2 divided by the kth term, which is k plus 3 over k into k plus 1. And this complicated expression can be simplified, and it can be written as k plus 4 over k plus 1 into k plus 2 times k into k plus 1 over k plus 3. You can simplify it like this. I hope so this is clear, because this is from basic mathematics. Okay, so let's cancel the terms. K plus 1 can be cancelled with k plus 1. Okay, and then simplifying the remaining terms, we will have in the numerator k square plus 4k, and in the denominator we will have k square plus 4k plus k plus 6. You can perform these calculations by yourself, I hope so. So if you look at this expression, this fraction, you can easily see that in numerator we have k square plus 4k, and in denominator we have k square plus 4k plus something else, which shows that denominator is actually greater than the numerator. So what will be the result of this? This expression will be less than 1. It's our observation from very young age that if we have a numerator which is less than the denominator, the answer of the fraction will be less than 1. So what do we have? We have ak plus 1, the quotient of ak plus 1 with ak less than 1, and from here you can write ak plus 1 is less than ak by performing a simple algebraic manipulation step. Okay, you can reach here. And what does it show? It shows that every succeeding term is less than its preceding term. So this helps us to understand that the size of the terms of this series is actually decreasing. Okay, so from here we can simply say that condition 1 is now satisfied. First condition is now satisfied. So what is left for us? We need to check only whether the limiting value of the series terms is approaching 0 or not. Let's see how will it behave. The general term of the series, as you can see from here, is an, or you can call it ak because we are using the index k. By the way, these are dummy indices, you can simply replace them by any other, but let's write it ak. So we have k plus 3 over k into k plus 1. Let's see its limit. How will it work as n approaches, or sorry, k approaches infinity? K approaches infinity. So taking k as common from the numerator, we have 1 plus 3 over k, and then k into k plus 1. K will cancel away with k in the numerator, and then you simply put the value of k as infinity, and after simplifying step you can simply reach at this 0. How? Because in the numerator you will have 1 and in the denominator you will have infinity, and we know that when something is divided by infinity, some very large number, our answer gets closer and closer to 0. Okay, so condition 2 is also satisfied by this series. C2 is also satisfied. And what does that mean? It means this series is also convergent. Alright students, so far we have seen the examples of convergent series. Okay, now we have taken a series which will diverge, and you will see that in a moment. So let's take the quotient of two consecutive terms of this series to see whether the size of the terms are decreasing or not. Okay, so let's take the quotient an plus 1th term divided by an term. This will be equal to n plus 1 to the power n plus 1 divided by n plus 1 factorial multiplied by n factorial divided by n to the power n. And if you simplify this expression, you know very well n plus 1 factorial is actually equal to n plus 1 into n factorial. Okay, so this n factorial will cancel with the 1 over here. Okay, let me write this. N plus 1 to the power n plus 1 over this n plus 1 factorial can be written as n plus 1 into n factorial multiplied by n factorial divided by n into n to the power n. So n factorial will cancel away with n factorial. So what do you have? You will have n plus 1 to the power n over n to the power n. You might ask me that it was n plus 1. Where is that remaining power 1? So it was actually cancelled with this one. Okay, and then you can write this as n plus 1 over n to the power n. So no matter what we have here as the exponent of this fraction, from inside you can easily conclude that overall answer of this expression will be greater than 1. How? If you look at the numerator, it is larger as compared to the denominator, and we know from our basic mathematics that if the numerator is greater than the denominator, our answer will be greater than 1. So if we have something which is greater than 1 and we take its power, our answer will be greater than 1 as well. So finally we have this expression to be greater than 1, which means that actually an plus 1 over an, the quotient of the consecutive terms of this series, is greater than 1, or you can say an plus 1 is greater than an. And what does that mean? It means that every succeeding term will be larger in size as compared to its preceding term. We wanted the series to behave in such a way that the size of terms should decrease, but it is the quite opposite. Here the size is actually increasing. So first condition of alternating series test is violated by this series. So finally we can say that this series is actually a divergent one. Alright students, here we have another example and we want to do the same to check or to investigate its convergence. But before that, I would like to tell you that it's totally up to you which condition you want to verify first. Why am I saying so? Because in this case, I'm going to check directly whether the second condition of alternating series test is being verified by this series or not. Okay, so let's see. And the second condition is that to check the limiting value of the general term of this series to see its behavior, whether it will approach 0 or not. Let's take the limiting value as n approaches infinity of the general term, which in this case is 3n over 4n minus 1. So what we are going to do is to take n as common from the denominator, and we will have 4 minus 1 over n. This n will cancel away with this one, okay, and then we simply apply the limit. What do we have? What will we have? We will have 3 over 4. How? Because 1 over n, when we will put infinity over here, this will become 0. Okay, so we will have 3 over 4. So what is the anomaly here? What's the problem here? The alternating series test wants us that the limiting value of your alternating series as n approaches infinity should be 0. But here the limit is actually non-zero. So this series is actually violating the second condition of alternating series test. So we can conclude that this series is actually a divergent one, right? Finally, students, we have a very simple example right before us. It's an alternating series. Let's see how it will behave. If I write any two consecutive terms of this series, they will be like, if I consider the first one to be n, the next term will be n plus 1. And we know very well that n is larger than n plus 1. Sorry, n plus 1 is larger than n, which means that the size is actually increasing rather than decreasing. So we have enough reasons to call this series a divergent one. But if you are still curious to investigate whether this series will satisfy the second condition, you can see that if I take the limiting value of this series as n approaches infinity, that will give us infinity rather than 0. So both conditions are being violated by this series. Okay, so this series is actually a divergent one. Okay, thank you so much for watching the complete video.
It's a proven fact that generosity makes you a happy person. So please be generous, subscribe my channel and hit the bell icon so that you don't miss any update.